Thanks, welcome. Who wants to build an embedded system? Who wants to use Python to build an embedded system? Okay, you're in the right place. The story so far, hardware is cheap. Specifically, the price difference between 8-bit and 32-bit processors is small and dwindling. That means there are more and more places we can use Python. That board has a 700 megahertz processor, a GPU, Ethernet, USB, 256 megs of RAM, and is perfect for running Python. It's called Raspberry Pi, and it costs $35. My premise is that programmers develop faster with Linux and Python than a real-time embedded operating system in C. The tools and documentation are much better, even when the documentation is the source. Just considering Python-capable systems, hardware resources can vary widely. I'm going to use 3 examples for this talk: electronic kiosks, routers, and thermostats. We have one problem. Linux distributions are designed for desktops, not embedded systems. The solution is use the pieces you can from a Linux distribution and use Python to build the rest. The first step is to choose the right distribution for your product. Kiosks usually have PC-class hardware, a screen, an x86 processor, a touchscreen or pointing device, and tens of gigabytes of storage. But there are some important differences. A desktop has one user and lots of applications. A kiosk has one application and lots of users. Kiosks have no human administrator. All configuration and upgrades must be automatic. Ubuntu has great support for PC hardware and gives you a number of choices for building your user interface. You can use a traditional toolkit, like Qt or GTK, or if you want to build your interface the web way, you can use the kiosk mode of Firefox or Chromium. Fedora also has great PC hardware support and could be a good choice. Ubuntu's advantage is that it's based on Debian, and the Debian project has packaged a lot more software than Fedora. So it is more likely that the software you want is already packaged. Further, Debian packages are more granular than Fedora packages. So if you're tight on space, it is a lot easier to slim down your storage requirements by removing packages than by digging into the individual packages and tearing out what you don't need. Debian becomes a better choice than Ubuntu if you don't need to support the latest PC hardware and desktop environments. For example, if you don't need a compositing window manager, Debian may be a better choice. The core Ubuntu components, both the kernel and the user space runtime code, are always on the leading edge, but that can mean those components aren't as portable as the core components of Debian. This is a chart of the CPU architectures Debian supports. I don't expect you to read it, but by contrast, Ubuntu supports x86 and one flavor of ARM. And if you need to slim your system down further, the mdebian project is a set of build tools that allow you to create your own Debian-based distribution with only the parts you need. This can save you a tremendous amount of time over manually trying to find packages or parts of packages that you can throw out. For a thermostat, the hardware design must be low cost. Nevertheless, inexpensive system-on-chip designs mean that Python is still feasible. The challenge of these designs is often related to minimizing the amount of secondary storage. For this kind of system, you'll probably want to start with a kernel and add pieces, instead of starting with a distribution and removing pieces. For the smallest embedded systems, BusyBox is a good choice. BusyBox is an implementation of the core Linux utilities made to be as small as possible. People often use it with a custom-built kernel, and newlib, a scaled-down C library, to create very small custom distributions. How does the Linux boot process work? How do you build software for non-x86 processors? How do I use a different C library? How do I make a custom Linux distribution? Linux from Scratch and its companion Cross Linux from Scratch are book-based Linux distributions that explain issues like creating and using a cross-compilation toolchain, building custom kernels, using unusual bootloaders, and customizing the boot process. They are excellent resources for anyone who wants to build embedded systems with Linux. If you're building from scratch, you will know exactly how your system works. But if you're using a desktop Linux distribution, The next step will be to find all the software that assumes it is running on a desktop and remove it, replace it, or code around it with Python. This can be a significant amount of work, but it helps a lot if you know where to look. I'll now talk about several areas of system software which frequently need modifications for embedded systems. First, I'll talk about 3 ways to do automatic upgrades. This is ideal for small systems that run off of RAM instead of off a disk or flash. The first step is the running system downloads a script. The script downloads a file system image and writes it to secondary storage. You reboot, and then the new image is loaded from secondary storage to RAM, and your upgrade is done. You might have a configuration partition you need to deal with or migrate some local settings forward, but that's the gist. And of course, this approach works for other archive formats like tarballs. For systems that run off secondary storage, a more complicated approach is needed. You have 2 partitions that each contain a complete system. You boot from one partition, upgrade the other, and then toggle the bootloader so that on the next boot, you boot the upgraded partition. This is called ping pong because every time you upgrade, the bootloader toggles which partition is booted. Downsides of this approach are that you need enough space for 2 system images on secondary storage, and you need to be able to download a complete system image. apt is Debian's package tool, and in many ways what makes Debian Debian. The advantage of using this approach, and it's a big one, is that you only download the packages that need upgrading instead of a complete system image. But using apt for upgrading embedded systems is complicated because of inherent desktop assumptions of apt. Debian packaging scripts, if they don't know what to do, can appeal to a human for help via the user interface of the upgrade application. The theory behind Debian configuration is that the human administrator is responsible for configuration, and only with the administrator's approval can packages change the configuration. This is great if you don't want your operating system upgrade to munge your carefully constructed Apache configuration. But this approach causes problems for systems that don't have a human administrator. Some other disadvantages of using apt in an embedded system is that the Debian packages don't support downgrades, and each package has its own set of scripts, and both the scripts from the old and the new software will run during an upgrade. This needs careful testing. The good news is that you can customize and automate the upgrade process using the Python apt library, and you can pre-answer questions that you know packaging scripts will ask. On a big system, it can be difficult to foresee which software you will need to upgrade. For that reason, you want to make sure that crusty, obsolete software that you are upgrading does not control the upgrade process. You want it to do the minimum, pull down some new bits, and run them. In that way, you can ensure that the new software you are upgrading to controls the upgrade process. And that software can be written so that it can upgrade whatever pieces it needs to, even if that means figuring out how to patch the bootloader's file system driver. So we've picked our distribution, we have a plan for upgrades. What other system software do we need to think about? Time is hard. Dates are difficult. Be wary of code related to dates and times. This is an area notorious for bugs, but is especially true when you are adapting desktop code to an embedded system. I'll talk about some of these problems. Avoid time zones if possible. Wristwatches do. First, there are a huge number of time zones. Just creating the user interface for specifying a time zone is not trivial. Second, governments change the rules regarding time zones frequently and often with little notice. Embedded systems either need to have a reliable, timely source of time zone information, or they should ignore time zones completely. GPS time does not use leap seconds. The current offset between GPS time and UTC is 15 seconds, but that offset will change over time. This is almost right. In Linux, elapsed time has no value. Linux does not have direct support for elapsed time. Applications get the system time and do their own calculations. Applications expect to be able to do this. And that will often work, but not always. The problem is, in Linux, time is implemented as a single global counter, and a privileged process can set the time whenever it wants. Depending on how much the time is adjusted, different assumptions about time break. For adjustments under half a second, time is slewed. The amount of time in a second is made longer or shorter for a time. For adjustments of more than half a second, system time immediately jumps forward or back. This affects timeouts and cron jobs. Why are all of the hourly jobs running at once? Because time jumped forward an hour. Time can be quite off depending on whether you have been taking good care of the hardware clock. On many Linux systems, the hardware clock is only set on shutdown. If you shut down uncleanly, the clock doesn't get set, and you'll have a big time jump in your future. Be very careful about setting the time. Don't manage Network Manager. Desktop systems use Network Manager to control a set of network interfaces, choosing the best one as connectivity changes over time. This approach may work if your embedded system roams across networks, phones, ebook readers, tablets. However, many embedded systems, routers, thermostats, set-top boxes, act more like servers than clients, and it's not appropriate to bring up and down network interfaces every time there is a brief connectivity outage. For these systems, the older IF up-down interface from Debian may be a lot more appropriate. Right or wrong, if you're using Ubuntu or Debian, you have inherited the desktop security model. As a result, as you are automating away configuration changes, you will need root privileges. Sudo can be configured to automatically give root privileges to a select list of commands. And this is often the easiest way to handle the privilege escalation that is required when you are automating changes in configuration. So we've picked our distribution. We have thought about how to avoid the assumptions of the desktop. Now we need to write some code. I want to talk about a software design issue that is particularly prevalent in embedded system software. This is going to be the most abstract part of my talk, so to talk about something concrete, I want to ask everybody, who likes frameworks? Yeah. Who prefers libraries? Okay, we'll come back to this. I want everyone to write portable code in Python. Wait, isn't Python code automatically portable? I haven't seen near and far pointers. I haven't seen endian macros in Python code. I haven't seen 36-bit words. So Python is portable across processors, but there's more than one type of portability. The kind of portability I'm talking about is creating a single source space for a range of products, which is very common in embedded systems. A common core functionality, but with somewhat varying features and a variety of hardware. On the feature side, maybe there's a basic model and a professional model. The hardware may have different sensors, different network interfaces, even different user interfaces. This kind of portability is about keeping the code maintainable as you add support for new hardware platforms and independent feature sets. The naive way to accommodate a range of products in a single source space is the if statement. You just write your code, and when you get to a difference between the products, you write something like this slide. That works. So what's the problem? The problem is that every place where something product-dependent happens, your core code must have knowledge of the behavior of every product. This is not maintainable. We can do much better. We'd really like to be able to work on the core code without seeing the complexity of all the product varieties. An obvious first step is to move the product-specific code into separate modules. This is a little bit better. The model-specific code has been moved into model-specific modules. We have contained the complexity a bit. But this style of code has problems. The common code is dependent on all of the model-specific code. This kind of dependency fan-out makes testing difficult. As we add products, this pattern will be repeated in more and more places. Nevertheless, that approach can work, as long as your products are similar enough that they all use the same interface. But it can be a bit of a trick to find that interface, and the interface may need to change over time, which can produce a lot of churn in your product-specific code. So why is this so hard? What are we doing wrong? Let's look at that code again. The problem is we have core code depending on the details of our products. If we want to have a stable interface, we need our code to depend on the commonalities, not the differences. In other words, we need to turn the code inside out. We need the product-specific code to depend on the core code. Here we have the product module calling into the core code. We avoid the problem of trying to find a common interface for all of our products by inverting the call graph and making the core code be the interface. Another way to think about this is we have taken our core code, our application, and turned it from a framework into a library. As a result, now all of our ugly product-specific and hardware-specific code is hidden. Finally, we can write core code that is completely ignorant of these details. Why does this work? The trick is, by turning the code inside out, we found a way to hide the right thing. The key to writing modular code is figuring out what you should hide. If you're having trouble designing a modular interface, focus on what you need to hide. When writing embedded system software, the trick is usually to hide the details of your hardware. A good way to do that is to turn the core of your application from a framework into a library. Choose your distributions, avoid the assumptions of the desktop, and write portable code. These ideas about structuring code for portability are not mine. I stole them. If you want to steal them too, read these papers. Use Linux where you can, and use Python for the rest. Write better embedded systems faster. I'm happy to answer questions.
I know this talk was specifically about Linux, but have you experience with FreeBSD as the platform, and what are your thoughts on it?
I don't have personal experience with FreeBSD, no. Okay, thank you.
Is there I have another question? Yeah.
This one.
Thanks, that was very interesting. I was wondering, because you brought up the issue of time moving around, and I guess I haven't had the experience of my global time being changed on me randomly. Can you perhaps talk about when that sort of thing happens? And yeah.
The time when it can take you by surprise is if you have a product that intermittently connects to the network. On Ubuntu, at least, when you connect to the internet, it will automatically set the time for you. So if you're not expecting that, it can be quite a surprise.
Thanks.
Yep.
I have a question here.
Hi.
I know you specifically talked about Ubuntu and Debian, and I think you were kind of concentrating more on long-running systems, and you were talking about automating the admin tasks. But have you had experience with like smaller distributions like Armstrong or the open embedded distributions?
I haven't. The last time I looked at them, it wasn't appropriate for my product, and so I can't speak to them.
Okay.
Is there any other question? We still have maybe 5 more minutes.
So one of the things that you mentioned was portability between products. Have you considered testing products for capability instead of just for product A versus product B? So, for instance, you could say like, does this product have a camera? If so, then, do something.
Sure, sure. I think detecting, when you can detect capabilities, detect hardware, that often is better than trying to configure it. But you still run into the same problems of having code that needs to be able to deal with not having a camera or having a camera, for instance.
Hi. Did you experiment with Gen 2? It's almost Linux from scratch.
No, I haven't. That would be another interesting approach to try. Do they support a lot of different processors?
Yeah, I mean, because they only have the package manager only has compiled recipes, basically, so they can support pretty much anything that GCC supports.
Mm-hmm.
But, okay, thanks.
Yep.
Hi, you mentioned about using Debian's app system.
Yes.
Do you have any experience, or did you toy around with the app build package in Debian? It's sort of along the same lines of Gen 2, where app downloads the source and then compiles it with whatever flags or optimizations you want.
I haven't used apt-build, no.
Okay.
Thanks. Yes.
Do you have any experience on power consumption running Python on an embedded, and how it compares to something else?
Nope. I've only worked with systems that run on power mains for this.
I think that it's gonna be almost time, so thank you very much.
Thank you. Thank you.